So hello everyone, this is lecture 10 for the nuclear physics. In the last lecture we were discussing some questions based on the basic properties of nuclei. So today also we will discuss some more questions, and in the next lecture we will discuss questions based on radioactivity. So today's lecture is gonna be a little bit short. So let's see. First question is this graph is given. This is binding energy per nucleon, and this is your atomic number or mass number is given, and corresponding to these nuclei it is given. So binding energy per nuclei versus mass number curve for nuclei is shown in the figure WXYZ. R4 nuclei indicated on the diagram. Check whether energy is released or absorbed in the process given below. So we have to check in all these four processes A, B, C, D that energy will release or it will be absorbed. So let's check for the Y to 2Z. So Y is disintegrating into the 2Z plus Z. So how can we find this? So we just need to find the binding energy difference, and that will give us the means energy difference will give us that energy will be absorbed or means removed, emitted. So it will be daughter nuclei binding energy minus binding energy of the parent nuclei. So this will be Z plus Z means for this one and for this one that will be daughter nuclei minus binding energy of parent nuclei. So for daughter it will be Z. So for Z we will see that it is 30 mass number and 5 is the binding energy per nucleon. So there are 2 Z, so that will be 60. There will be mass, means 60 nucleons will be there, and for 60 it is binding energy per nucleon. So 5 multiplied by 60 will give you total. So 60 multiplied by 5 minus for parent it is Y. So for Y it is mass number 60 and binding energy is 8.5. So 60 multiplied by 8.5. So just subtract this, and this difference came out to be negative, means energy will be absorbed. Similarly you will find for all these three, if energy came out to be, this difference came out to be positive, means energy is emitted, and if this difference is negative, that means energy is absorbed. So that's how you can find for all these three also. Let's see next question. This is again a binding energy per nucleon curve is given. So this is your mass number, this is 100, this is 200, this is 2, 4, 6 and 8. Assume that binding energy per nucleon versus A is as shown in the figure above. Use this plot and answer yes or no for the given statements below. So fusion of two nuclei with mass number lying in the range 1 to 50 will release energy. So there is fusion of two nuclei which are lying in this range, means 1 to 50, there will be some 50, and these two are lying here and they fused to give some third nuclei. So there will be energy release or not, so we need to find that. Then again next question is fusion of so let's see for the first one. So if two nuclei are there and they have 1 to 50, if you take any two nuclei which have mass number between these, then sum will always remain less than 100. So all the three will lie here. All the three nuclei, means two before the fusion and the one after the fusion, all three will lie here. And you will see that all have the same binding energy. So difference will be 0 in the binding energy difference. So there will be no energy released or absorbed. So that will be 0. Means there will be no energy release in the A option. Next is fusion of two nuclei with A is lying 51 to 100. Now 51 to 100, here it is lying. So if you take two nuclei, then the after fusion, that third nuclei which is formed after daughter nuclei will be lying somewhere here. So that will have this very large binding energy per nucleon. So that minus that will give you some positive difference between the binding energy. That means energy will be released. So you can calculate that. That will give you positive. Next is fission of, so there will be yes for this, B. Now third is fission of nucleus A 100 to 200 will release energy when broken into two equal fragments. Now A is lying between 100 to 200. Now it will be lying somewhere here and it will disintegrate into two nuclei. So they are asking that if energy will release or not. So if it is disintegrate, then it will lie, means both the two nuclei which are disintegrated after fission will lie here. So daughter nuclei will have the less binding energy as compared to the parent nuclei. That means difference of the binding energy will be negative, means energy must be absorbed, so there will be no energy release for this transition or the fission. Next is fission of means same question is there, but A is lying between 200 and 260. So it is 200 and 260, and they are asking if energy is released. So see, if now you divide this into two nuclei, so they are saying that it will be into the two equal fragments. So if it is two equal fragments, then after this 200 to 260 will divide, they both after fission will lie here. So daughter nuclei have the high binding energy and parent have less. So daughter minus parent will give you the positive difference. So energy will be released in this D option. So this you must remember that it is two equal fragments. That's why we are getting these results. So I hope you get this. So you can solve this. So there are many questions will be asked from these type of questions. So you must pay attention to this. Next is the binding energy per nucleon is 8.5 mega electron volt for A120 and is 7.6 for A equal to 240. Suppose a nucleus with A240 breaks into two nuclei of nearly equal mass. Calculate the energy released in the process. So this 240 is break into two equal parts, 120, 120. We need to check if energy is released and it is how much. So binding difference would be daughter nuclei minus the parent nuclei. So 120, for 120 it is 8.5. So 128.5 plus 128.5 minus 240 multiply it is given 7.6 for 240. Now this difference came out to be positive, means this amount of energy will be released. Next is the electric charge density rho r inside a heavy spherical nucleus as a function of distance r from the center may be approximated most closely by. So in the inside a nucleus, how charge density vary from the center, we already discussed this. So this will be this D option, means initially this density will remain constant, but see this bump is not normally there, but we can see this, that this is exponentially decreasing. So these two are matching very well with the result as we discussed. So this will be your correct answer. Initially it will remain constant, at the boundary it will be like this, dropping like this. So that is the thing. Now last question. Identify the correct statements regarding a nucleus. Uncertainty in the momentum of a proton in a nucleus is roughly 10 to the 5 times uncertainty in electron in the ground state of hydrogen atom. So we need to find the uncertainty ratio for the proton and the hydrogen atom electron. So we know this, how you can find for the uncertainty principle using that. Delta P will be h cut by 2 multiplied del x. So del x will be nothing but size of the proton, that will be 2r. Now this is h cut by 4r, and this is approximately radius of the proton, that is radius of nuclei, means for the hydrogen atom it will be proton will simply nuclei, so r nuclei, and for electron it will be radius of the atom. So you have these two, so just find the ratio of this momentum uncertainty, that will give you this r atom by r nuclei. So r atom is, we know it is around 1 angstrom and nuclei is 1 Fermi. So this will give you 10 to the 5, means first option is correct. Second is volume of nucleus grows linearly with the number of nucleons in it, so this is correct, as we know that volume is 4 upon 3 pi r cube and r is r naught a 1 upon 3. This will give you this r naught a, so it is linearly proportional to a, this volume energy. So sorry, volume. Third is energy of gamma rays due to the excitation of nucleus can be of order of mega electron volt. So as in the atom we see that there are energy levels and there is energy emitted when this transition will be there. So similarly in the nucleus also we have the energy levels, and when nucleons go to the transition, then there will be a energy, means there will be a gamma particle emitted with some energy, and that energy is around the mega electron volt. So this C option is also true. And D is Fe56 is the most stable nuclei. So as we have seen in the binding energy curve, so for the Fe56 we have the maximum binding energy per nucleon, so that means it is the most stable nuclei. So these all four are correct. So that's all for today. In the next lecture we will discuss the question based on radioactivity. So thank you everyone.